Okay, so welcome back to this next video in which we're discussing group theory. Okay, so we want to try and create a group algebra now from this set of symbols that we've created before. Okay, so this set of symbols consisted of this sand timer-like symbol, this backwards 4 symbol, this backwards 5 symbol. Then what we want to do is draw this composition table for this, or the Cayley table for it. So here is our composition law. Right, okay, so we'd already discussed that we want an identity element, and we've chosen that the sand timer symbol should be our identity element. So when you compose sand timer with any of these other symbols, it's just going to give that symbol back again. So sand timer composed with any other symbol, so where this symbol is on the right here, is going to give that symbol back again. And similarly, that x composed with sand timer, okay, should also equal that symbol back again. So x composed with sand timer should equal x. So any of these composed with sand timer should equal that symbol back again. Okay, so this is the identity property. Okay, so this is the first axiom obeyed. Now we want it to try and obey associativity and inverses. Now, there is only one group algebra which has 3 symbols in it. There's only one group algebra that you can make if you have a set containing 3 symbols like this. And it involves putting backwards 4 composed with backwards 4 as backwards 5, backwards 4 composed with backwards 5 as being sand timer, and backwards 5 composed with backwards 4 as being sand timer, and then finally backwards 5 composed with backwards 5 we need to equal backwards 4. Okay, so let's try and prove that this is going to obey the other properties of being a group. Okay, so let's try and prove that it is going to obey the associative property. So we want to prove that it's going to obey associativity. Right, okay, so this could be a lot of very hard work if we weren't going to be slightly clever about this. So, what associativity involves proving is that no matter which symbols you put in for A, B, and C, so A, B, and C can be any elements of our set. Okay, so this one could be backwards 4, this one could be backwards 5, this one could be another backwards 5. So there's 3 things that this one could be, 3 things that this one could be, and 3 things that this one could be. And you need to check that this is always, absolutely always equal to A composed with B composed with C. And I repeat, I could not stress more how non-trivial that is. It is not trivial that if you take an element A and compose that with an element B, you'll get an answer. Take that answer and compose it with C, you'll get another answer, your final answer. It's not trivial that that will be equal to, if you take B, compose it with C, get some strange answer, then take that answer and take A and compose it with that answer to get your final answer. It's not trivial that that will be the same thing, basically. Okay, so to emphasize that, let's just put in some numbers here and I'll show you what it means on the composition table. Okay, so let's put in backwards 4 composed with backwards 4, like this, composed with backwards 5, and then we want this to be equal to backwards 4 composed with backwards 4 composed with 5, and it is. I promise you it is, because this is a group. But let me show you why it's not trivial. So, here is this backwards 4 here, okay? And we are composing this with another backwards 4 over here. Okay, and I'm going to label that one up in green. So, we'll have this one up in green. And we're getting this structure out, which is backwards 4 composed with backwards 4, which is here. Okay, and we're then taking that structure here, and we're then composing that. That's this blue one. We're then composing that with this turquoise structure here, which is over here, to get our final answer, which is down here. Whereas on this side, we are taking b, which in this case is this backwards 4 here, and it in this time is going to be represented by this one. We're composing that with backwards 5, which is in turquoise here, okay, to get backwards 4 composed with backwards 5, which is over here in the composition table, okay, and then what we're doing is then composing backwards 4 with that pink thing here, okay, which is, oh wait, let me get the right colours. So this one is now up here, and we're going to take backwards 4 again here, and we're going to get this answer as our final answer. So yes, they are the same place, but the entry you are looking at in the composition table is different. Yes, they're the same answer, but they're in different portions of the composition table, and it's not trivial that that is just going to happen to equal that, basically. That's the emphasis of that you are actually going to get different entries of the composition table from doing these two separate things, and you're requiring that those two entries are going to be the same, which of course in the general composition table where you've just made it up on the spot, they're not. Okay, so I hope that hasn't confused you too much. The main aim of that was to show you that the overall entry in this composition table you get to is different between these two, and therefore that it's not trivial that this one is going to equal this one, and you could dream up easily a composition table where they don't. Okay, so are we going to have to go through all 27 possibilities? Because there are 3 separate things you could put in here, 3 separate things you could put in here, 3 separate things you could put in here. So that makes 27 overall. Are we going to have to go through all 27? Well, no is the answer. We're going to have to go through 8. And the reason I can reduce it down to 8 is because if any one of A, B, or C is equal to, well, sorry, not is an element of, is equal to sound timer. So if any one of them is equal to the sound timer, then my claim is it's instantly trivial. So for instance, if A is equal to the sound timer, then it doesn't matter what B and C are. They can be any other element of the set. They could even be other sound timers. They can be any element of the set, and it's just trivial that the associative law is true. The reason being, look at this. Okay, so we'll stick in the identity element for our A here, and now if we look at this, the identity composed with B is just going to equal B, because this is the identity, and anything composed with the identity is equal to itself. So then the answer to this is B, so we're asking what is B composed with C here. Similarly over here, we're asking what is B composed with C composed with the identity here. Okay, and that obviously is again just going to equal B composed with C, because the identity composed with all of this is just going to equal all of this, which is B composed with C. And the same thing happens if you were to stick the identity in for B or the identity in for C. No matter what A and B were, it would always work out, basically. So the identity being any one of these elements simplifies matters. So let me just show that. So let's say now that the identity is going to take the place of B here. So we've got A composed with the identity, and then compose that in brackets with C, and we want it to equal A composed with the identity composed with C. And again, A composed with the identity is just the A, and then we've got A composed with C, and on this side the identity composed with C is just C, so this is A composed with C. And the same thing will happen if you put the identity in for C. No matter what A and B are, if the C is the identity, then the whole thing becomes trivial. Okay? Because on this side, B composed with the identity is just going to equal B, so that makes this side A composed with B, and on this side, A composed with B composed with the identity is just going to be equal to A composed with B. So, if any of A, B, and C is the identity, then it's instantly trivial. Therefore, we might as well assume that none of them are the identity, okay, which means now that A, B, and C are either going to be backwards 4 or they're going to be backwards 5. Right, so that means that each one only has 2 options. So now there's only 8 things that we need to check. So let's go through these in some orderly fashion. So, backwards 4 composed with backwards 4 composed with backwards 4. We'll start off with the most natural one. Okay? Is this equal to backwards 4 composed with backwards 4 composed with backwards 4? Now that actually isn't as trivial as it looks, because backwards 4 composed with backwards 4, okay, that's going to equal backwards 5, as we can see from our composition table. So we are actually asking, is backwards 5 composed with backwards 4 equal to backwards 4 composed with backwards 5? So we're asking, is it commutative with respect to 4 and 5? Okay, or 4 composed with 5. Now, the answer is yes, okay, but it's not trivial that that is true. Yes, this group actually happens to be commutative with regards to every multiplication. Now, not every multiplication in every group is going to be commutative, so not all groups have all multiplications commutative like this group, okay? So, this wasn't as trivial as it looked, basically. Okay, that this worked wasn't so trivial. Okay, so 4 composed with 5 is going to be sand timer, and 5 composed with 4 is equal to sand timer. Okay, now I just want to, I think it's probably a good point to add in a little bit of terminology. When you have a group that is commutative with regards to every multiplication, i.e. for all A and B, A composed with B is equal to B composed with A, then you call that thing a commutative group, okay? Or it's also known as an abelian group, after the famous mathematician Abel. Okay, so it's also called an abelian group. Okay, so that's the name for a group which has a symmetric in this diagonal line composition table. Okay, right, so we've now checked 1, okay, 1 out of the 8, so let's continue on. So we'll keep the first 2 the same. We'll keep A and B as backwards 4, and we'll alter the third one, the C, to a backwards 5. So this is backwards 4 composed with backwards 4, then composed with 5. And we want to see, is this equal to backwards 4 composed with backwards 4 composed with backwards 5, like so. Okay, so backwards 4 composed with backwards 4 is backwards 5. So we've got that backwards 5 composed with backwards 5 needs to equal backwards 4 composed with, now what is backwards 4 composed with backwards 5? Well, that's going to again be sand timer. So we need to make sure, whoops, what am I doing here? Okay, we need to make sure that backwards 5 composed with backwards 5 is equal to backwards 4 composed with sand timer. Well, we know that backwards 4 composed with sand timer is going to equal backwards 4. Now, backwards 5 composed with backwards 5 is also equal to backwards 4. So that holds true. Okay, so there's number 2 down. Right, now let's keep A the same and alter B. So we'll alter B to the other option, which is backwards 5. And then we'll start off C as being backwards 4. Okay, and we want to make sure that this is equal to backwards 4 composed with backwards 5 composed with backwards 4. Now we can see that this is going to be true because our group is commutative, so we don't have to check that because of the commutative property. So backwards 4 composed with backwards 5 is the same as backwards 5 composed with backwards 4, so we could swap this for backwards 4 composed with backwards 5, okay, and then we can swap the backwards 4 composed with all of this around to turn it into this. So that's true by commutativity. Excellent. It's nice when occasionally we don't have to do them by brute force and we can do them by using brains. Okay, so backwards 4 composed with backwards 5 composed with backwards 5 now, and we want to make sure that that is equal to backwards 4 composed with backwards 5 composed with backwards 5. Okay, so up to here, backwards 5 composed with backwards 5 is backwards 4. Okay, so this becomes backwards 4 composed with backwards 4. Okay, and on this side, backwards 4 composed with backwards 5 is sand timer. Okay, so sand timer composed with backwards 5 is just going to give backwards 5, and then we have to check that backwards 4 composed with backwards 4 is equal to backwards 5, and that is true. So the fourth one is now checked. So we now change A to backwards 5. Okay, so backwards 5, and then the other two will set initially to backwards 4. So you've got backwards 5 composed with backwards 4 composed with backwards 4, and we want to make sure that that is backwards 5 composed with backwards 4 composed with backwards 4. Okay, right. So let's put these in. So backwards 5 composed with backwards 4 is equal to sand timer. Sand timer composed with backwards 4 is just going to equal backwards 4. Then we've got backwards 4 composed with backwards 4, which is backwards 5. And then we've got backwards 5 composed with backwards 5, which then is backwards 4. So that one's worked as well. So there goes the fifth one now. And then let's do the sixth one. So backwards 5 composed with backwards 4 composed with backwards 5 needs to equal backwards 5 composed with backwards 4 composed with backwards 5, like so. Okay, now is that one we can do with commutativity? Yes, we can. We can swap round the 4 and the 5 here to get backwards 5 composed with backwards 4, like we have on this side, and then we can swap the two bigger things around to turn it into this one. So the sixth one's done by commutativity, and then finally, well actually not finally, penultimately, we'll get backwards 5 composed with backwards 5 composed with backwards 4 needs to equal backwards 5 composed with backwards 5 composed with backwards 4, like so. Okay, so backwards 5 composed with backwards 5 is going to give backwards 4. So we'll get backwards 4 composed with backwards 4, okay, which is equal to backwards 5. So this overall on this side equals backwards 5. Then on this side we'll get backwards 5 composed with backwards 4 is equal to sand timer, and then we've got backwards 5 times sand timer, which is just equal to backwards 5. Okay, so that's that one, and then finally the final one is just backwards 5 composed with backwards 5, and then finally composed with backwards 5 is then equal to backwards 5 composed with backwards 5 composed with backwards 5. Okay, and that again is true just now by commutativity of this group. Okay, so commutativity can help you if you've got that. If a group is commutative, it helps you prove that it's associative in a little bit. Okay, right. Then the final thing we want to make sure of is inverses. Okay, now the identity is its own inverse, so you don't need an inverse for the identity, because remember, inverses, all an inverse is we need an element, okay? For every element x in the set, you need another element x inverse, which will compose with it to make the identity, and the identity more generally is often abbreviated by E, okay? So, if you take the identity and compose it with itself, then you will get the identity, because the identity always takes anything to itself. So basically the identity is its own inverse. So all we need to make sure is that backwards 4 has an inverse, okay, and also that backwards 5 has an inverse. So we need an element that composes with backwards 4 to make the identity. So here is backwards 4, and the only thing that it composes with to make the identity is backwards 5. Okay, so we think that backwards 4 and backwards 5 are inverses of one another. So backwards 5 seems to be the inverse for backwards 4. Okay, and I should have said also we need to make sure that also x inverse composed with x like this way round is also equal to the identity. And I should also say that people often drop the composition symbol and they just write things juxtaposed like this to mean compose this one with this one. So, if you have an element with its inverse, okay, then if you compose the two of them together in either order, that should equal to the identity. So let's make sure that backwards 4 composed with backwards 5 is equal to the identity, and that also backwards 5 composed with backwards 4 is equal to the identity. Well, we know that instantly because of the fact that the group is commutative. Okay, right, so we know that backwards 5 is the inverse of backwards 4. Now let's make sure that backwards 5 itself has an inverse, which is going to be backwards 4. So backwards 5 will become the identity when it's composed with backwards 4. Okay, so backwards 4 is backwards 5's inverse, and backwards 5 is backwards 4's inverse. Okay, now that always is true, because if one element is the inverse of another element, then that other element is its inverse. So if we, for instance, just look at this relationship, x composed with its inverse is equal to the identity, and also x inverse composed with x is equal to the identity. So if we ask what is the inverse of the element x inverse, okay, well that has to be x, because all we're looking for is an element which will compose with x inverse either way to give the identity, and x satisfies that definition basically. Look, x here will compose with x inverse either way to give the identity, so it is x inverse's inverse. Okay, so that proves that this is a group.